Hello, Tigers. Today we are going to work with exponential growth and decay. So let's get excited to learn something new. I can explain the meaning of a constant a, the y-intercept, and the constant b of an exponential function when the function models a real-world situation. So today we're going to be working with the real-world situation, otherwise known as growth and decay. I can distinguish between exponential functions that model exponential growth and exponential decay when presented with a real-world problem. So today also you're going to identify when you're looking at an equation that is growth and when you're looking at an equation that is decay. Exponential growth, y is equal to a times b raised to the x power for a is greater than 0 and b is greater than 1. The base is the growth factor. So the b, or the base, is going to be your growth. Compound interest, paying interest on the principal and the interest that has already been earned. In the past, you've learned the formula I is equal to PRT, or interest is equal to principal times rate times time. Well, that is a simple interest formula. And so what that means is that if you borrow money or if you invest money, that you are only making interest on the principal. Well, in a compound interest formula, which is what we're going to be working with today, then you're actually making interest on the interest, and unfortunately, you're owing money on the interest. So that's the difference between the two. Interest period, the length of time over which interest is calculated, and normally we think of interest period just kind of in general, we're going to think of it in terms of a year, and then how it's related to how the different ways to calculate are proportional to a year. Decay factor, y is equal to a times the quantity b raised to the x power for a is greater than 0, and the b is actually between 0 and 1. That's what this means. The base is the decay factor. Excuse me. Identify the initial amount a and the growth factor b in each exponential function. So we've got the function of x is equal to 13 times 4 raised to the x power. So a is 13 and b is 4 for the first example. For the second example then, a is equal to 100 and b is equal to 2.53. So we're just kind of getting ourselves acquainted with the formula. Each percent is an annual interest rate. I mentioned the simple interest formula. We talked about I is equal to PRT. Well, the R is the rate. In the formula, y is equal to a times b raised to the x power. What value would you use for b? So if you were substituting this in, there's a couple of steps to get there. That's why I like that we're going to kind of separate it out first. So if I am, for example, making money off of my money, I want to make 100% plus I want to make 17% of my own money. So we start with 100%, so I'm going to make 100%, meaning all of what I invested or unfortunately what I borrowed, plus 17%. So 100% plus 17% gives me 117%. However, when I go to plug it into the formula, I'm not going to plug in the percent. I'm going to change that to a decimal by dividing by 100. So the number that I would put in to the formula is 1.17. We're going to do the same thing here with 5.39%. Once again, it's going to be 100% of whatever I borrowed or what I'm investing, plus 5.39% gives me 105.39, but I can't plug in a percent into an equation. I have to change it into a decimal first. So to do that, we're going to divide by 100 or move the decimal back 2 places. So the number that I would input is as follows. So if you get stuck when you're trying to plug in numbers to the formula, go back to this slide and this will help you. Assume each interest rate below is an annual interest rate. Find the interest rate for an account that is compounded quarterly and monthly. Round to the nearest thousandths place if necessary. So we know that annual means what? Year, right? Annual is going to be talking about the year. So if it's 4%, we want to figure out it's going to be compounded quarterly and monthly. So this is actually two different parts. So I'm going to put quarterly, and then also we'll come back and do monthly. So that means that I'm going to compound 4 times a year. So if I'm going to compound 4 times a year, I simply take 4% and I divide by 4. So that means that every quarter, then my interest is it's going to compound 1%. If I'm doing that monthly, then once again, I'm going to take my 4%, but this time I'm going to divide by how many months are in the year. 4 divided by 12, which is going to give me 0.33, it says thousandths place, so 3.3333%. We want to make sure we're rounding accurately. So by quarterly, it would be 1%. If it was monthly, then it would be 0.333%. So you can see that there's quite a bit of change there for depending on if I'm going to do this monthly or if I'm going to do it quarterly. All right, let's do the same thing here with 5.75. So if we're going to compound that quarterly, 5.75 divided by 4, and that's going to give us 1.4375. We want to round to the nearest thousandths place because that's what our directions say to do. So our answer then is 1.438%. Why don't you pause the video and you can calculate the interest on 5.75% if it was compounded by month. Welcome back. So although the number is smaller with monthly, you have to remember that you're doing that 12 times a year as opposed to just doing that 4 times a year. So you're actually going to make more money if it's compounded monthly rather than compounded quarterly. Find the balance in each account. Now the good stuff. So now we're going to kind of put this all together. $1,000 is deposited in a college fund that pays 7.2% compounded annually. Find the balance after 5 years. So the first thing I want to do is write our formula. And then we just have to kind of get our bearings on what the numbers mean. So I would say let A equal initial amount. In other words, my investment. B is going to be I need to find the rate. So basically this is going to be our growth factor. Because if I invest money, then I obviously want it to grow. X in the formula is going to be the number of interest periods. In other words, how many times am I compounding this particular money? How often are we going to do that, considering that it's 5 years? And then the last is the amount in the account at the end of that term. So the first thing we're going to do, I'm going to go back to my formula. Y is equal to A times B raised to the X power. So I've invested $1,000. Like to keep my equal signs lined up into the account. And just kind of a side note, it's 7.2%. So this is what we were talking about earlier. We're going to take 100% and we're going to add 7.2%. And so I get 107.2%. But when I plug it into the formula, I don't plug in 107.2. I'm going to divide by 100 or move the decimal back 2 places. So then in the formula, it's going to be 1.072. And that's going to be my base. 1.072. And then raised to, it does say annually, and it gives us the amount in years. So all we have to do is raise that to the 5th power. So we're going to record. I'm going to do 1,000 here, and then 1.072 to the 5th power, and I'm just going to kind of start writing some numbers. You guys can punch that in your calculator in case you don't believe me. But I went beyond the thousands place. I just want to make sure that I am as close to the correct answer as possible. So I just kind of went out, 6 places there. There's not an exact amount, but definitely go out 4, 5, 6 places. Find a good place to round. As far as money is concerned, we know that money is rounded to the nearest hundredths place. So my final answer should be $1,415.71. So after 5 years, we have gained a profit of what? $415.71. By adding 100%, we didn't just figure out the interest, we included the initial amount rather than trying to find the interest and then go back and add it later. So we kind of simplified our life by putting it in the original formula. Now we're going to do the same problem, but instead of having it compounded in 5 years, and by the year we're going to compound it quarterly. So we're going to see how that changes. So the same account is compounded quarterly instead of annually. What is the balance in 5 years? So I'm going to write my formula. So we still initially deposited $1,000 into the account. And then our interest rate, this is where it's going to change a little bit. So the first thing that we're going to do is take that 7.2%. Having to move my computer because I don't want to become detached to the computer. Give me just a second. Sorry for the delay, you guys, but yes, it did come unplugged, so I'm trying to make sure that you can hear me. I'm sure some of you are saying, I'd rather not listen to you, Ms. McDaniel. Okay, so 7.2%, and we're going to go ahead, because it's quarterly, we want to divide that by 4. And when I divide 7.2 divided by 4, I end up with 1.8%. So now we know that we're going to change that. We have to add the 100%. So we have 100 plus 1.8%, which gives me 101.8%. Divide by 100 or move the decimal back 2 places. So we've got 101.8. And that's going to be the amount that I input into my B. So 1.018. Now we have to be careful because we're no longer just compounding it once a year for 5 years. We remember it was quarterly, so now we have to take 5 and multiply that by 4, and that's going to give us 20 interest periods. So we're going to plug 20 in for our exponent. So we should end up with y is equal to 1,000 times 1.01 to the 20th power is 1.428747. And again, we're talking about money. So once you round, you want to go to the hundredths place, $1,428.75. All right, now we're just going to do some simple identify the decay factor in each function. The decay factor is what is happening to the equation. So this is kind of like what we talked about in the video where we had the photograph. And so if we're talking about a photograph, then if it's 90%, then it would be decreasing at a rate of 90%. 90% of that, 90% of the next one, 90%. So this is going to be our decay factor, or 0.4. And then our decay factor in the second one then would be the 0.56, or we could kind of think of that as 56%. Identify each function as exponential growth or exponential decay. Well, once again, we're looking at our B term. So this is going to be a growth. And the reason it's a growth is because it's greater than 1. 0.59, you may have guessed, that one's going to be a decay because it's less than 1. Notice I didn't say negative, but actually it's going to be between 0 and 1. So less than 1, but greater than 0. Write an exponential function to model the situation. Find each amount after the specified time. Suppose the population of a certain endangered species has decreased 2.4% each year. Suppose there were 60 of these animals in a given area in 1999. How many animals were still alive in 2005? So now, instead of a growth, then you're going to see a decay. You even see the word decreased. So I'm going to start off, before I even talk about the formula, because it's a decrease, then the first thing you're going to do is take 100%, because we're talking about 100% of the population, but we're going to subtract 2.4%. Because another way to figure out the percent is to subtract it from 100 and then figure out the percent of that particular number. So 100, in other words, instead of taking 2.4% and then subtracting it from the original, then we can just subtract it from 100% and we'll get exactly the same answer. So it actually makes it a little bit easier. So 100 minus 2.4, that's going to give us 97.6%. So in other words, we're calculating 97.6% of our original numbers, or 60 of our 60 animals. So we've got 97.6, so we want to change that into a rate. Move the decimal back 2 places, so it's 0.976. Now I'm going to go to my list. So let A equal our initial population. Let B equal our decay factor. Last time it was our growth. This time it's our decay. And then X, or our exponent, that's going to be the number of years. Last time it was our interest period, but now we're talking about population, so it's going to be the difference between 2005 and 1999, which gives us 6 years. So we'll come back and use that number in just a minute. And then Y is going to be the number of animals remaining. In other words, how many animals were there in 2005? Okay. All right, so we started off with 60, and our rate is 0.976. And then we already said that our years is going to be 6. So 0.976 raised to the 6th power is going to give you this nice nasty number. Aren't we glad we have a calculator for that? Multiply by 60. Our final answer should be 51.862 animals, but we can't have a weird number for animals, so we're going to round that up to 52 animals remain. I hope you enjoyed your lesson on exponential growth and decay.